All right, welcome back, guys. So, we're doing chapter 11 today, which is the t-test for a sample that is tested twice. So, a group that goes through two different treatments. So, the last thing that we talked about in chapter 10 was two separate groups, so independent samples, two separate groups who then go through the same treatment. This is one group that is going through two different treatments. So you are testing them twice, so repeated measures. So let's go ahead and hop over. So, t-test for two related samples. They're related because it's the same sample, or rather it's the same group, and you are testing them twice, therefore getting two samples that are related to one another because they come from the same population, or the same sample. Okay. So, your book starts out with an example talking about how dogs are adopted when they're in a shelter, finding that when you attach a picture of the dog and make it very appealing, that they're more likely to get adopted, dogs that are kept in shelters. And they use an example of a research study that looked at pit bulls, which have a bad rep and are typically not often adopted because of preconceptions of it being an aggressive dog. And so what they did in this study was they had a group of participants look at two different pictures of a pit bull. One being just a picture of a pit bull without a handler, just sitting there looking all doggy. And then a second picture where the dog is with a pit bull, the same pit bull is with a child. So they first look at the pit bull by itself, and then they give a rating on whether or not the likelihood that they would adopt this dog. And then the second picture that they show is the picture with a kid, so a pit bull with a kid. And then they ask them to rate again, how likely are you to adopt this dog? And what they find is that they increase their likelihood in wanting to adopt the dog after they see the picture of the pit bull with the boy, meaning the child. So the idea is that, they changed their rating because it was more appealing or more attractive to them seeing the dog with a child, right? Obviously, the dog is not attacking the child. It's like a cute picture of them standing next to each other. So this reminded me of something that I found out about service dogs. So in one of my special topics classes that I did for PTSD and the brain, at the very end of the semester, I had the Southeastern guide dogs come and give like a demo with their doggies, which is really cool. So service dogs are for those who cannot see, but then you also have, which would actually, be guide dogs. Service dogs then can also be for veterans diagnosed with PTSD and having symptoms, or I think the third category for this particular group where they provide dogs for is a service dog for children who are having difficulty. Because I think it's actually a fairly large range of difficulties that they can have. So they provide the service for free, which is really nice. So, you basically sign up with them, you go through an interview process, you hopefully get matched with a doggy. And so here are some of the doggies. These are not all puppies. But it was really interesting to find out that there is a bias against, not from somebody who has a service or a guide dog, but from how the public views service and guide dogs, that the public sees a dog that is the beige, like nice tan golden retriever or lab, see them much more favorably than a black lab. So they actually end up having more puppies that are, the golden tan or beige color, because people don't view the black lab as favorable out in public, right? So, these are service dogs and can actually, if it's a proper service dog, they can go into restaurants and other places where an emotional support animal is not allowed to go. And so the whole idea is not to disrupt the public, but just to help the human that the dog is with. And so it was really interesting. They have a hard time well, not a, actually, I don't know if they say that they have a hard time, but what they're trying to do is change how people view black labs in particular that are service dogs. So I think this was a group of 6 dogs, and it was half and half. So I think 3 black labs. You can see the other one over here, and I forget what where the third one is here. But they actually, when they do these outreach programs, like what they did for my class, they came, they did a demo, they demonstrated what the dogs are capable of. They intentionally bring black labs as well to show, like, hey, they're just as cute and capable as the beige ones, right, that people seem to favor. So it's kind of part of their program, actually, that they want to change people's perception just based on their the coat color, right? So in the if we had done this in class, I would have showed you some cute videos, but check out the comments below. I have a website for the Southeastern Guide Dogs. So they're actually like local, like an hour south of Tampa. Really, really cool organization. And they have, I put in the comments, there's a YouTube video that they use to promote their organization, which is called PIP, which is really cute, animated, maybe like 5-minute videos. So very cute. Check it out if you have the chance, especially if you want to get like a little teary-eyed. I think it's great. So let me move on to what we're actually going to talk about today. So the idea is actually, let me just go back. So the idea with that study that I mentioned with a pit bull and the 2 pictures that they look at, it's the same group of participants that are tested twice. So repeated measures, they are going through, the treatment is repeated on them in 2 different ways, right? Treatment 1, or what we call treatment, was the first image of the pit bull without a handler. The second treatment would be the second picture, and see how people react to that. So coming back to this that I showed you guys in chapter 10, chapter 10 was a between subjects design, right? When we talk about 2 different independent groups, hence we call it independent measures. So 2 separate groups, you cannot mix those 2 groups together. They're separate independent ones. Whereas in chapter 11 that we're going to talk today about, it's the same group, but is tested twice. So 2 different treatments, such as before and after therapy, like a baseline measure versus then how they do after your experiment. It can be a longitudinal study where you take multiple measurements, right? If you're taking more than 2, then you can't just use the t-test. You're going to have to use statistical methods that you learn in Stats 2. But for our purposes, same group, measure twice, you can do the t-test for the same, for a repeated measures design. So I'm going to walk through it, but honestly, none of this is really new stuff. There's just one little change that's happening. That's why chapter 8 was so important, because it sets up hypothesis testing. What is the t-test? How is the t-test differently than the z-score? And then from there, all of these are t-tests with like minor little changes depending on if you have 1 group, 2 groups, or 1 group just tested against a population, which would be single sample t-test, which was the first one that we talked about. Okay. So the major change here, if we're talking about 1 group being tested twice, we are not going to be using just 1 score. We're very specifically going to be using different scores with everything. So here you can see what a typical setup would look like. Start thinking about this, because the week after Thanksgiving, we are going to start dealing with SPSS. So the way that you organize your SPSS table is going to be important. Here you have your participants, right? When you guys input your data, like I said, do not put the names in. Give them a code, right? Participant 1, participant 2, or participant A, participant B, however you want to go about it. You have 1 column just for the number of your participants, because then each row will represent for that participant the 2 treatments that they underwent. If you had something like 5 treatments, right, you just kept taking time points every month, checking in on them, then you would have a column for each check-in point. And again, a t-test is not going to be good enough for that. You're going to have to do something like an ANOVA, which is not what we're going to talk about in this class. But you can see here treatment 1, treatment 2, right? And it has to be something you can directly take a difference from, compare those two treatments, right? So in the case of what some of you guys were doing with questionnaires, you can't compare two different questionnaires, right? You can't compare a score on the state anxiety compared to personality trait, right? So it has to be something that you can repeat again and test again. So, and I'll get to that in a second. So to compare, the goal here when we're using these different scores for one sample or one group tested twice is we want to compare those two treatments, such as before and after, like I mentioned, baseline versus treatment, or you just have two different things that you can directly compare, right? It is important here, directly compare. It has to be numbers that you're taking a difference from that makes sense. So a lot of you are doing the research project of do different personalities handle uncertainty differently, right? So here, this is not something that you can treat as a within subjects design, right? Even though everyone is going through the same treatment, meaning you're giving them a personality questionnaire, you're giving them an uncertainty questionnaire. What you're interested in when you give them that personality questionnaire, you're going to look at, okay, if someone scores high on neuroticism, how do they treat uncertainty? And if somebody scores low on neuroticism, how do they deal with uncertainty? So inevitably, you're going to start treating those as two separate groups because you're not like extroverted one day and introverted the next day, right? I mean, realistically, we all kind of like fluctuate a little bit, right? You might have like a day where you're like super extroverted or super neurotic, but generally personality is a stable construct, right? Ideally, if you took this every month, every year, each person would kind of stay in that same rating that they would give you. So it's a stable trait. So we can't test someone twice, like we can't treat someone as a low neuroticism and high neuroticism. So it has to be treated as a between subjects design, right? Either you're extroverted or introverted, high neuroticism, low neuroticism. And like I mentioned, you can't compare two different questionnaires. Now, things that you can use this test within subjects design, some of you are taking heart rate data, and you explicitly said, I'm going to take it I'm going to take it before, during, and after, or you only said before and after, which is great. And that's testing the same person twice, right? Heart rate before, heart rate after. You do a within samples or repeated measures t-test, and you see, did it go up, right? So they're perfectly fine to do that. I had you guys integrate if you're doing an experiment, integrate the state and trait anxiety inventory. So there I said, give them the state anxiety portion before and after, so that it's, again, you're doing it twice. So you can look at the difference. Are they anxious before the experiment, or did the experiment make them more anxious? Right, so there you can do a within subjects t-test, but you're going to be doing it separately on the whatever personality trait you decided to do. You're going to separate them into different groups and see, does the low neuroticism group do this? Does the high neuroticism group do this? We're having to artificially do this because if you did the proper analysis for that study, you would do a correlational analysis. But we're not covering correlational analysis in this class. That's for Stats 2. So we're having to artificially create two separate groups by looking at their scores and giving someone, you're going to be low trait on this or high trait on this. And I'll talk to you guys, one-on-one more about this, on how to actually code your data. But I just want to point that out because some of you are collecting a lot of different data, and we're going to be treating them differently depending on what it is. Okay, so we have two different scores, right? First score, second score. This might actually be second, like in time, right? And you can see here there's a difference of 3 increase, 4 increase, 2 increase, no increase, and 6 increase. So we can create another column called our difference, And everything for this t-test is going to deal with different scores, not the raw scores. So you just make a new column, -5, +20, +20, +20, right? These are the guys that you're going to work with. So the formula is going to be the same as chapter 9, which was single sample t-test. That's why I'm saying this chapter is going to end up being rather short and not a lot of new conceptual parts, except for knowing how to treat your data. Is it within? Is it between? Can you do a single sample? There'll be a few things at the end that I mentioned, differences between within and between. Differences, but so everything we're going to be using are different scores, not raw scores. So all calculations have to be done with these different scores. Okay. Introduce the idea of different scores. Now let's look into hypothesis testing. How would we do this? So again, 2 related samples. Our null hypothesis is also going to deal with different scores. So we're not just saying that the population is 0 or the population mean, we're saying the difference of the population means, because you're getting 2 different treatment values, but you're saying treatment 1 is not going to be different than treatment 2. That's your null hypothesis. So the difference between those means is 0, alternative, different from 0. So again, your column here where you can calculate different scores, that's going to be what you actually end up dealing with and what you plug into your calculations. So coming back to our test statistic, whether that's a t statistic or a z statistic, it's always the same setup. It's the actual difference between the sample you collected, like the sample mean, and what the population would be. Or if you're not using, an actual population value, some type of logical makes sense kind of thing you're comparing it against. With in the denominator, the expected difference. The expected difference is something like the standard deviation, the standard error, the estimated standard error, right? So this setup is always going to be the same, and it's not going to be different for this. All we're doing here is that these are all going to be different scores. So the different scores of the means that you're collecting, different scores of the 2 populations. If you treated the population twice, right, you're going to measure the different scores between those treatments. And now we have a double subscript here, which is a little crazy. Be careful with your subscripts. So this is not just the standard error. This is going to be the standard error of the sample mean difference. So standard error just like before, and the formula is actually the same. But again, we're not using raw scores, raw mean scores. We're going to be using difference scores here. So again, the standard error of the difference, standard error for the sample mean difference. So in order to calculate that, you would need the variance, right? To calculate your standard error, usually we have to start with either sum of squares or our variance here, though, so we can plug that in. So just like before, variance for a sample, don't forget the n-1, our sum of squares, which the sum of squares is going to come from the different scores, and I'll show that in a couple slides. We can plug in the variance into our standard mean, or not standard mean, standard error formula. So standard error for the sample mean difference. So again, same formula, doesn't change. Variance over how large your sample is, take the square root. And again, just be careful with your notation. Then you can plug this guy in here and ta-da! All right, so let's do an example of that. So this is an example from your book. I always try to put the number up here so that you can work through that if you want to go through the process yourself. So the study example here is it better to study the night before an exam or get more sleep before the night before an exam, right? So study or sleep, because both might be beneficial, right? You can use more time to study, cram more in your brain, but sleep is important because that's how you actually can retain a lot of the information. Healthy body, healthy brain. So what we're going to be looking at is below average sleep versus above average sleep, right? So if they got a lot of sleep, did they do better academically, meaning on the test? Or if they got less than average sleep, did they do worse or better, right? So the null hypothesis is that there's no difference between the two treatments. The alternative would be that sleep versus studying results in different academic performances. So our difference in the population means are not zero. Select alpha 0.05, two tails. All right, step 2, locate the critical region. And since we're in the T world now, we're talking about degrees of freedom. So you have to find that. In this sample, it was 8 people who were tested. That means your degrees of freedom is 7, 8 minus 1. You can look this up in the T distribution table, which is in the appendix B.2, I think. So there you find your column for two-tail test and alpha 0.05, and then you run down the table, or you run down the column until you hit DF7, and that ends up being the critical value of 2.365. So this is the value to beat if you're going to reject the null hypothesis. Okay, so we're going to be go through the whole process. These are the actual values that came out of doing this test. You can see participant here, A through H. Was that 8 people? Yeah. Oh yeah, we saw that in the setup before. So 8 people. And mind you, I should have noted that here. So 2 different treatments, right? But obviously on 2 different nights, because you can only sleep one night below or above average. So they did multiple tests with them on 2 different nights. So on one night they got above average sleep, on another night they got below average sleep. But because it's hours of sleep, you can directly compare the 2 values and calculate a difference scores. So bam, 3-hour difference there. Or not 3 hours, sorry. This is not hours here, this is their academic performance. So a 3-point difference on their academic performance. You can see everybody here. You can go calculate the sum of all of these guys. And because we're working with raw scores and we're not given the sum of squares, we actually have to calculate it ourselves, and we can do that. So this is flashback to using the definitional or the computational formula for sum of squares. So if we calculate the mean, right, so we have the sum here, the sum of the different scores, 32, divide by how many people we have, 8. That gives us an average mean difference. So then we see it's 4. We could actually use the definitional formula if we want. For simplicity here, because we're talking about sum of squares, we can just do this nice squaring here and then end up using both of these. So here, the book walks you through the computational formula. Plug those guys in, then get your variance. Variance is SS over n minus 1, or degrees of freedom. So what you got for your sum of squares over the degrees of freedom, 16. Then you can go and calculate the standard error for the sample mean difference, right? Standard error for the sample mean difference. You have your variance, from here 16, plug that in, divide by how many people you have, 1.41. Then you plug that into your t statistic. Down here, 1.41. And here we're dealing with a hypothetical, right? We're going to say it's 0. So basically 4 divided by 1.41 gives you 2.84. So take a moment, 2.84, does that lead you to reject the null hypothesis? Or is this t not large enough? So the critical value we had before was 2 point something, 2.365. So in fact, 2.84 is larger than 2.365, so we can reject the null hypothesis, and we can say, oh, your sleep does have an effect, right? How much sleep you get has an effect on academic performance. I'll show the write-up of that on I think in on the next slide actually. I'll show how you would write that up. But remember, you do your 4 steps of hypothesis testing. What is step 5, right? Step 5 is how strong is my effect? Because the hypothesis test doesn't tell you how strong it is. It only says it was significantly different. So to figure out how strong the treatment was, you have to calculate effect size. You can do this through Cohen's d. Here, I noted in red what is different from like all the formulas that we had before. So here you're again using difference scores. So the mean difference, sample mean difference, over a puny little standard deviation, nothing too crazy down here. And the R-square also doesn't change. Luckily, one thing doesn't change between all the t tests that we do. If you're in the t world, then it's going to be the same formula. So as long as you have a t and you know the size of your sample, plug that in. Plug that in, you get your R-squared. So a note about write-up, even though we're doing two-tailed hypothesis testing, you always want to make sure what direction the actual effect was. So calculations are almost identical to single sample t-tests, super cool. We don't need to make major changes. We're just dealing with difference scores now. Make sure that you do report first what the actual mean was for the different groups, or you can just, I always like to put as much information as possible. You can also just put the mean difference, or you can report their means and the mean difference. Then you report on the t-test, and then you want to make sure you address what direction did it go through. Like, did more sleep increase academic performance, or did more sleep decrease academic performance, right? That's important to know. So this is how we might write it up. Experiencing a night of below average sleep increased academic problems the following day by an average of 4 points, right? So this is that mean difference here, right, that we put up here in Cohen's d. We give a standard deviation. The treatment effect was statistically significant. T, in parentheses, your degrees of freedom. Report on the t statistic. Say what alpha level you used and whether it was significant. And then you either report Cohen's d or R-squared. Here R-squared was 0.5. That's a very strong effect. So not only significant, strong effect as well. But you can see here, experiencing I have below average sleep, right? So this is one of those treatments. Increased academic problems. I beforehand was talking about improving academic performance, but you can also list it this way, right? So this is where you have to go back to your research question and make sure that you formulate it correctly in here. But make sure you do talk about what direction it went. Did it increase or did it decrease? Even if you're doing a two-tailed hypothesis, talk about which tail it actually went into. Okay, we're just like flying through this. So now the last part is to talk about the pros and cons of each of these tests. So often you can actually use either design, but there are pros and cons, and we'll walk through this. But you know, as long as conceptually it makes sense, then you can use kind of either of these analysis tools. But I'll address some points where it's kind of hard to like justify using one of them. So I highlighted in purple repeated, because repeated measures t-test is actually a little bit better to do if you can. So one aspect to address are the number of subjects you have. If you don't have a lot of people, repeated measure t-test is the way to go. So you guys, you know, some of you only recruited 4 or 5 people, which is what I told you to do, right? Because, you know, we only have 1 semester to do this. But to be on the safe side, you would want to run a repeated measures t-test, not an independent measures t-test. And I'll show you in a minute why. So if you only have a handful of observations, you can basically test them repeatedly, right? If you want to get all of the data that you can out of them, just keep making them do things, and then you use a repeated measures t-test to see, you know, did my treatment change something significantly? If a study changes over time, you would really want to use that repeated measures t-test. So time moves on, right? We can take multiple samples over time. If we have a research study that looks at learning in particular, or a longitudinal study, childhood development, or drug abuse progress, or something like that, something where there's this change over time, repeated measures is usually the way to go, because you're testing repeatedly on the same person. Individual differences. So when you have individual differences and you're trying to not deal with that and eliminate it, right? You want to say all people are the same, like all of their one brain structure does the same thing, then using a repeated measures t-test is going to be advantageous. So obviously the problem here is that if that's what you want to study, a repeated measures t-test is not going to work, which in the case of what you guys did with differences in personalities, that is not something that you can treat repeatedly, right? It has to end up being different personalities is an independent measure. You're either low or high in extroversion or introversion. So the advantage of repeated measures really comes from the idea that you're dealing with much less variance, right? So this is showing an independent measures study. We have 2 treatments, and we have 3 people who did one treatment and 3 people who did another treatment. The numbers are actually going to be identical if we treat it as a repeated measures study. Here now, treatment 1, 3 people do, but then those same 3 people do treatment 2. So when you're doing an independent measures t-test, you have to deal, I was about to point at the screen, you have to deal with 2 different variances, right? And then you have to pool the variance. And it's weighted based on which has the larger sample, and it's that like crazy calculation you have to do. Whereas for repeated measures, you're doing a different score, and your variance actually ends up being a lot smaller because it's the same people. You're not dealing with a whole nother group of people who have a separate degree of variability. So if you actually calculated their variance, again, these are all the same numbers, but how you calculate it for the different tests is different. So if you look at the variance and the standard error, repeated measures is much smaller, which is great. We want our test statistic to have a small variance or small variability, small standard error, because that ends up making a difference for the t-statistic. Here, if we have those same 6 numbers for an independent measures t-test, our t is not significant. 0.87, in no world is that really going to be a significant, I can reject the null hypothesis. Whereas over here, same 6 numbers, but because it's treated as a within subjects design, less variability, therefore stronger or more distinct shift with your treatment, right? Variability kind of narrows those distributions, and you can see -4, that is huge. In pretty much any world, that is going to be significant, right? Where we can reject the null hypothesis. So simple demonstration of the same numbers treated with a different t-test coming up with different values. So that also leads me to the last part, power. You're actually going to have an advantage doing a repeated measures t-test. You're going to have more power. And that goes exactly with what I was mentioning before. Because you have low variability, because you're testing less people, you have a lower standard error, which in the end gives you a greater statistical power, which is always good. That's what we want to aim for. We want things to be, we want to reject the null hypothesis, we want strong effect sizes, and we want a lot of power. Okay, things where instead we're better off using independent measures design or independent measures t-test. Time-related factors. So sometimes if you are testing someone on 1 month and then you bring them back into the lab and you test them again, a lot of time has passed and various things can actually influence, you have maybe small variability, but that variability might be due to something entirely different, right? So one, maybe participants got better over time, regardless of the treatment, just passage of time. Maybe they learned and then they did better the second time around. That wasn't because of your treatment, it's just because they got better and they learned something. Other environmental factors can come into play, the weather, the season, right? If you're doing it like on a regular monthly basis, maybe with women, where they are in their menstrual cycle can affect it, right? Order effects too. So experience can influence the person their second time around. They're like, oh no, I got this. Like, I know how to deal with this now. So one way to eliminate that one in particular is counterbalancing, right? So some of you, I talked about this. If you had two different treatments, like they looked at a scary video and then a relaxing video, or a scary script and then a relaxing script, I told some of you to make sure that you counterbalance, meaning you don't always show everybody first the scary and then the calming. Counterbalance and show half of your people the other order, right? Some people are going to start with the relaxing video and then see the scary video. So if possible, counterbalance because of order effects. What else do I have in here? Not always possible. Yeah, so sometimes one's just inevitably, you can't change the order because one's a baseline measure, right? And in that case, there's not much you can do. Yeah, so if you expect strong time or order effects, you're safer to go with independent measures design. I think there's one more. Oh, yeah. So this is kind of a mix between matched subjects design. If you want the advantage of repeated measures, but in reality, it's a independent measures design, you can do this like hybrid, which is called matched subjects design. So two separate samples, independent measures, but participants are matched one-to-one. So one person in one group is matched to a person in the other group, and then they are treated as if it was repeated. So for example, if you are trying to look at verbal learning, you could match someone, group 1 has an IQ of 120, because we might think intelligence influences your verbal learning. So one person in one group with IQ of 120 gets matched with a person in the second group who also has an IQ of 120, so that you can eliminate the confound of intelligence that might help you actually, that, you know, that might be a reason why some people might be better or worse in verbal learning. So then you could confidently say, okay, it was my treatment that happened and not differences in my people. So that's one way to do that. Here, the t-test that you would actually use is the repeated measures design, because you're treating it like a repeated measures design, right? So person 1 and person 2 are treated as if like the same thing's happening, or rather two different things are happening to the same person. So kind of a unique situation. We won't be really dealing with this because so many of you do have a independent measures set up. To get more statistical power, ideally we convert it to a repeated measures, but unfortunately we really can't do the matched subjects design. So we're going to be doing a mix of both repeated and independent, depending on the data that you collected in your research study. And that was chapter 11. Boom. Okay, guys. That was actually our last chapter. After this, it's dealing with SPSS, figuring out how to structure your data, put it into SPSS, learn to click which test you're going to do, and then start learning how to write up the results section, and then wrap up the paper. Okay, guys. I will see you soon. Bye.